Hello, this is the Disaster Recovery Pro, and this is my video series discussing key topics in information technology with a focus on disaster recovery and business continuity. In today's presentation, we're going to take on a slightly more technical topic than normal. We're going to take a look at database backup and recovery. And rather than get too deep into the technical details, we're going to keep it at a high level and focus on what information you need to know to develop a recovery solution and or plan a recovery test. Let's start by taking a high-level look at the architecture of a database engine with the goal in mind to identify those components that are going to be critical to formulating a backup and recovery plan. At the top level, we have the database server. This is the physical or virtual server that the database software runs on, and this includes the operating system that runs on that server. It should be noted that in modern cloud environments, your database may be running on a virtual server, or it may be running as a serverless instance. In this case, the cloud service provider has abstracted away the need for an actual server, and you just manage it at the database level. With some commercial database engines, you have a concept of an instance, and for our purposes, you can think of an instance as just a collection of related databases. And then below the instance level, you have your individual databases, and each database is a collection of managed data that can either be tightly structured in the case of a relational database or loosely structured in the case of a NoSQL database. At the risk of oversimplifying what could be a very complex topic, we're going to focus on three high-level components for each database that are important to backup and recovery. First, we have the database storage. This is the actual live data that comprises the database, and it will live either in data files within a file system or on dedicated raw disk devices, depending on your database engine. Next is our database backups. These can either be backups directly to disk on the database server, or they can be backed up directly to commercial backup software using various APIs. These backups are a full, complete snapshot of the database at the point in time when the backup is taken. You can use these backups to recover your database, but you can only recover the database to the state it was in at the exact point in time when the backup was taken. This means that you do not have the option of restoring your database to the state it was in at a point in time between your backups. So let's say if you back up your databases once a day at midnight, you won't have the option of rolling that database back to the state that it was in at noon that day. This is where our third component comes into play, and that's your transaction logs. Transaction logs are basically a record of all the operations that have been performed on a database in the order that they're performed. The transaction logs will effectively allow you to fast forward or rewind your database to a specific point in time. So in the context of disaster recovery, they will be used to allow you to recover your database to a point in time between your regular database backups. These logs are typically written as data files on the database server's file system or to a section of cloud storage in a cloud provider's environment. For a large, high-volume database, these logs can add up to a lot of storage, so they are usually only kept on a temporary basis and will need to be rotated out. In a server-based implementation, you can make sure that you capture these logs in your regular file system backups and make arrangements to clean them up based on whatever your backup schedule is. Let's take a look at the steps you would need to do to recover a database from backups in a traditional sense. Let's assume we're using a server-based implementation. We have a way to recover the servers, and then we have our database backups and transaction logs backed up. Since a database is live data that's subject to frequent change, a standard file system level backup is not sufficient to back up and be able to restore that data and have it in any kind of consistent usable state. Because of this, we back up and restore our databases separately from the server and its component file systems. And we use the transaction log mechanism to get a more granular point in time. In order to restore a database, we do need to know exactly what point in time we need to recover the database to. That will determine which of the full database backups we're going to need to recover the database, and what range of transaction logs we're going to have to be able to restore or get access to otherwise in order to roll the database to the point in time that we need. So if we want to restore our database to the state it's in, say at noon on Wednesday, we'll need the database backup from the night before, and we'll need that day's transaction logs, at least the logs generated from the time that the backup was taken up until noon on Wednesday. This gives us a process that we can break down into 4 high-level steps. First, you'll need to either restore or rebuild the server that the database runs on. That includes the operating system and all file system data. Once the server is up, you're going to go to your database backups and restore the applicable full backup of that database. Then we need to take a look at our transaction logs and see if the restored file system already has the range of transaction logs we need to get to our point in time. And if necessary, we may need to go back to our file system backups and find the exact set of transaction logs that we need to bridge the time between the full backup and our desired point in time. Then once we've restored those transaction logs, we can replay the transaction logs to bring us forward or back to the desired point in time. That exact point in time typically determined by your recovery point objective or RPO, and any requirements by the application or application dependencies that the data belongs to. It should be noted that in virtualized environments, this process can be greatly simplified, since virtual machines can be backed up from a snapshot that represents the entire machine in the state that it's in at the time that the backup is taken. And if the database engine that you are using is virtualization aware, that database engine may be smart enough to start up in a last known good state when the virtual machine that it resides on is restored. And this is usually due to that transaction log mechanism that we discussed. So if the database is not in a 100% consistent state when the database engine starts up after a restore, it can use the transaction logs to incrementally roll back the last set of transactions until it gets to a state where it's consistent and able to start. From there, it is possible to use additional transaction logs to roll back the date further if you need an earlier point in time than the last known good. Another recovery strategy that can be used is what's called the warm standby or log shipping method. In this model, you'll have your live production database in one location and a duplicate of that server or database instance in another location as a standby. The live production server is the one that will actually process transactions, and as it processes transactions in response to queries, it will build up its transaction logs as a replayable record of those transactions. Then, on a periodic basis, depending on how active your database is, you can send or ship your latest transaction logs over to the standby server. The standby server can then ingest these new transaction logs and bring its database up to synchronization with the live production database. Again, how often this transfer occurs depends on how busy the database is and your recovery point objective requirements. For a busy database, logs may be sent over every 5 minutes. For a slower database, logs may be sent over, say, once an hour, assuming that this time period falls within the allowable data loss determined by your recovery point objective. In a model like this, you typically need to execute a set of manual steps in order to fail over from the production to the standby database, and that process would typically include ensuring that the production database is down and off the network, then switching the database from standby mode to production mode. Synchronization with other dependent applications may require you to roll back the database further, and you may also have to update your DNS and/or application settings to point to the standby server. It may be possible to automate some or all of this process using third-party automation or orchestration tools. Another common solution model is clustering, either active-passive or active-active modes. This type of solution is often referred to as high availability as well. In this model, you'll have 2 instances of your database that are peered together, and they will often be at different physical locations. When a change is made to the active database, that change will simultaneously be sent to the peer database for processing as well. Note that in this case, we're synchronizing the two databases when the operation or transaction occurs, rather than after the fact when we write a transaction log. In an active-passive model, one of the database peers will be designated as the active database, and all other instances in the cluster will be on standby. The active instance or node will be the one that will accept and process transactions, and those transactions will be written in parallel out to its peers. If a failure happens in the active node, the first available passive node can be promoted to active or primary status, and the database can continue processing transactions with little to no interruption in service. In an active-active configuration, all nodes or peers in the cluster will be active and able to accept transactions directly, and any transaction performed on any node is transmitted out to its peers for processing as well. In this case, if one node or instance has a failure and is no longer available, the other nodes in the cluster will already be up to date, and any new transactions or queries will be routed to the remaining nodes rather than the failed node, and the database will be able to continue to function with little to no interruption in service. Although in this case, the loss of an active node means that there will be a reduction in the capacity of the database to process queries. You'll note that while my diagram only shows 2 nodes in the cluster, you can have multiple nodes, 3, 4, as many as you want. The main advantage here is that in most cases, the cluster itself can manage failover and failure operations without the need for additional orchestration software. And in the case of an active cluster, actually make use of all the resources on both the active and standby systems, rather than have systems that are just sitting there waiting for a failover. There may also be technical limitations on a clustered solution, depending on the physical distance between nodes and the network latency between them. Too much latency may impede your cluster's ability to keep its nodes in sync with each other. So in summary, we can see that these basic recovery models can be applied to physical server implementations, virtualized server implementations, or even serverless cloud implementations. Especially in serverless cloud implementations, you may have different features that use different terminology, but those recovery models and strategies are still going to be close analogs to the ones that we've seen here. Most commercial database engines have transaction logging, which allows you not only to roll your database to a specific point in time, but in virtualized settings will allow a server to start up in its last known good state without much intervention. In some cases, you can use data replication as a replacement for backups and restores in order to move your database backups and your transaction logs to the recovery site. This doesn't affect the overall strategy per se, but it may impact and reduce the amount of time it takes to retrieve things like your backup files or your transaction logs. It's also important to know if your log shipping or clustered solution requires manual failover or failback steps, or if it can be automated and to what degree it can be automated. It's really critical to understand which backup, restore, or replication model you're using, as that's going to really determine your ability to meet your recovery's desired recovery time objective and recovery point objective. A backup and restore method is generally going to be slower than a recovery by log shipping, which will generally be slower than a recovery through clustering. So your recovery time and recovery point objectives will basically dictate which backup solution type is going to be necessary for your solution. And in the case where the technology solution you're currently using does not meet the recovery time and recovery point objectives, you'll need a high-level understanding of what each solution type is capable of in order to determine how you're going to bridge that gap between actual and desired objectives. Thanks for watching today's presentation. If you found this topic interesting and you want to learn more about disaster recovery and business continuity, you can help support the channel by leaving a comment to tell me what you thought about it, clicking like on the video, And most importantly, subscribe to the channel and click the notification bell so that you won't miss out on my next video. Your support and feedback is very important, so thank you for watching and supporting the channel, and have a great day.